Thank you. If you joined for the very first time, my name is Mahesh. I do these sessions on Friday for free for all of you because my mission in life to make sure that if I learn something, all of you can learn it, and especially AI because that's what I learned a little bit earlier than others. So I started working in AI in 2016. I will close to be 10 years, and sometimes I do miss like, hey, did I make the right choice? of starting this whole thing. But these Friday sessions just gives me a lot of act. So if you're here for the first time, that's me. I need not to talk about me a lot because I will be talking about neural networks today. One day I should just talk about me, or all of you should talk about yourself, but not today. Today we're going to talk about neural networks, and we'll focus on neural networks for next 45 minutes. I hope it is good. So let me tell you why neural networks are important, or why these tech concepts are important for product managers. The idea is that you want to learn latest greatest stuff, and there are people who are leading in the field. Andrew Karpathy, Andres Karpathy is another. It's a good influencer or a good researcher who has taken his personal time out, and he writes and he creates simple code, and then he go to podcast and talk about stuff. And generally what used to happen when I was at Google is we used to debate whatever Andre said, or there is another guy, Layakun, who also talks about like what's going to happen, what's happening. And we used to, this would be a good discussion for our lunch meetings or other things with our managers. And it just, there is always a meeting, but there is a way to show off also that you are cool and you're ready for a promotion. That's the behind the scenes. And if you want to judge somebody, you don't ask them questions like, hey, this or that. You just want to make sure that they understand the ecosystem as much as you do. So I was watching this one. This one just came out 13 days ago. I took this screenshot, so it should be 14 days ago. If you watch this, there is 137 times on how many times he talked about neural networks or the concepts of neural network. That means it's a 2 hour long session. Every minute you could think of something he threw where he talked about, oh, this is a local minima, oh, the gradient descent. But the gradient descent does not really work with the reinforcement learning. The gradient descent just goes over. And then you want to learn. He's very good, like he simplifies a lot of things, but then these terms come up and then you're like, maybe it's not for me. And your learning stops there. And my goal in the course or in this community is to demystify these concepts to you. Because to be honest, when I learned about first time these concepts, that was back in 2016. Andrew Nang had a course on deep learning then. Some of you may have done it. No disrespect to him. He's an awesome guy. He's done much more than anybody else did for all of us to learn. But that put me to sleep. I was like, dude, like he's just sitting on a room, the video is bad, and then his examples, and then I was like, dude, I just like this. I'm like, dude, I want to learn this. And that time I was a dev, so I needed to code these things, and I was like, I couldn't get it. So those are my triggers. That's why I thought it would be really good for this community to know. By the way, when you go and have these discussions with your engineering or your VPs, they have these concepts, they understand them in machine learning, and not having that understanding will exclude you, like this video excludes you from the community that's learning a little faster than you if you can't make sense of this video. Similarly, in the boardrooms, even though the topic is very different, even though what you're trying to decide is very different, when these terms are thrown, if you can't be in the room mentally because you can't understand some of these terms, you miss a lot in your career, in your product planning, in your product strategy, or your cross-functional collaborations. This was central to our course when we started course 2 or 3 years ago. But then I took it out of the course because it was getting very techy. So I thought it would be good community session. And then we will just put the video in the course. So I get this extra 1 hour to spend with you and teach you or talk about these technical concepts, which may not be directly related to your job, but I think are important. So don't take them as like urgent or mission critical, but important things. Okay. And even if you get 10, 15% today, and that helps you learn on your own later, is the goal today. By the way, they are so important that We even gave Joffrey a Nobel Prize. He got a Nobel Prize for inventing neural networks. So Turing Award, Nobel Prize, and Andrew talks about it. That means neural networks are important. Okay, I need not to talk about myself. You all know this is my LinkedIn. If you want to just send a request, I generally accept requests till I can. So do that. If you want these sessions, here is a form. Take a picture of it, fill the form. We will invite you automatically. So you get to not to worry about learning without us. With all that said, cameras on. If you have questions, just keep it to yourself. Nobody's going to answer them. Sorry, just if you have the question, put them in the chat. I will take most of them in the end, but let me land a lot of things in the beginning, because I have seen when people take me left and right, I can't land all the ideas. So let me go for 30 minutes, and then all of you can come with questions. And if you are part of the cohort, I will stay back in our TGF. So just hold on, let community people ask questions. If you're part of the cohort, we can get in a room after this call, and then you can ask me. I can ask me anything for the people who are in our course community. Okay, what's the agenda? We will talk about neural networks. We'll understand the lingo, and maybe we will not go to the limitations. Story of the day is mostly there was this person in one of the rooms, and we were discussing something on planning for 2025, where we want our team to be, what agent should we build. And suddenly somebody switched the conversation, which I hated, to how overshooting gradient descent. And then we spent 45 minutes. And after that, Riddhi turned around. They all left. And I never got my agenda, which was what agent should we build? And we had this 45-minute discussion on gradients and how they work and what is the shooting gradient problem. And everybody contributed to it because they were all having fun. Nobody wanted to really do what we wanted to. So I was frustrated because of that reason. But I looked at Riddhi, and Riddhi just started crying, saying, Mahesh, I don't belong to this team. Maybe this is not the right team for me. And which I was surprised, because the discussion these dude had for 45 minutes were not even relevant. The relevant element, and she was awesome. She knew how customers work. She was awesome with agents. She can plan, but now she wants to quit our team. And I wanted to avoid that for all of us, so that at least you know bare minimum, that you can hear the conversation and say, these are discussing something outside. I can bring them to the main point. But if you don't know, then you think maybe this is related because I don't even know the concepts. And that's what I'm trying to avoid today. With that all said, let's get started with neural networks. What are neural networks? Neural networks are a way to build models. What are models? Models are nothing but equations. So if neural networks are a way to build models, then models are equations, then everything is an equation. And those equations help us predict patterns or find patterns. The goal of machines or learning or artificial intelligence is to find patterns in data and then learn those patterns so that they can make prediction. The prediction can be what should be the next word in a sentence. The prediction could be what could be this customer will churn for your business or not churn, or this engine will stop or not. All these are prediction based on previous patterns. Model is nothing but a mathematical equation which can help you find the world patterns or represent the patterns of the world in the most accurate way. Everybody's like, let me just get out of this call. This is already above me. Okay, we will explain this. But the idea is simple, which is neural networks are nothing a representation of creating an equation, which is more like how our mind works, which can learn patterns in data. And those patterns are nothing but eventually behind the scenes are mathematical equation. And that's all we're going to learn today, how they represent information. Okay. So the simplest equation in the world is y is equal to x, which is, okay, if you want to predict whether we will go for movies or not, let's say this is no, this is yes, because machine understands 0 and 1. So I'm putting 0 and 1s. And the simplest equation to make that prediction whether I will watch a movie that's playing on a theater nearby or not is this one, where If the world was that simple that if there was a movie and I will watch it, then no matter the X is the value of the movie playing, right? So let's say X is like movie playing or not, right? And then you can have 0, 1, and simplest equation, then the pattern becomes, hey, if the movie is playing, if X is 1, then Y is 1. Mahesh always watches it. And if that's the world, then that's your model. And this model is always 100% accurate. If there's no movie playing, we don't go. So far, so good. You understood a model. Anybody says a model, now you know what it is. It's some mathematical equation which represents this pattern. If there is a simple world where there is a movie, then we can go and play it. Great. But it's not as simple as it, right? A movie can have a lot of parameters or a lot of inputs. So this is your input and this is your output or prediction. Output is the prediction and input is the variables that this prediction depends upon. But in the world, there are a lot of variables, right? So this was our life, me and my wife. If there was a Hindi movie, we lived in Seattle. Anybody from Seattle? Say yes. Awesome. People in Seattle, it rains a lot there, especially now, October, November, already raining maybe, Sanjay.
Yes.
Right. So what our best pastime was, there was cinema, and every time there was a movie, we will go for it. We didn't care. We just needed to kill time, and it was just comfortable way to kill time. So we lived in cinema when there was new kids. But then we got a boy. His name is Kabir. Kabir was 5 years old. So we will run this simulation. When I first time wrote this, Kabir is 5 year old, and we stopped watching going for movies because Kabir was like 1 to 5. Parents here can relate to it. You don't watch movies. You have a tragedy coming, a tragic movie running in your household all the time when your child are from 1 to 5. I hope my kids never watch this video. But, but once he turns 5, we can go back to movies. And now he's deciding which movies can we go for. And he learns the world is little complex now. It's not as simple as it was before because the X are different because we wanted to make sure that, hey, by the way, with Kabir also, we can be like that. But when he was 5, there was another problem we had. There was little Aryan. Aryan is 1 year old, but we are rich by this time. Another thing changed. The world is really complex. It's not as simple as it is. So the world is complex. We have another child, but we want to take him for movies and we want to go for movies. So our input variables changed. It was no more whether the movie was playing or not. It's movie playing or not. And let's just say Hindi movie because there's always movies playing. But Cinemark at that time only played limited time a Hindi movie. Otherwise, it's only English movies. We had few variables whether the Hindi movie is playing or not. So 0 and 1. Can we get babysitter for Aryan? Was the another variable for us to decide whether we will go to watch a movie or not. And then somehow I like trailers. And you can go on and on, which is like, can we get tickets before? Because we don't want it to go all the way, have a babysitter, and then realize that we can't get tickets, or we get tickets for this like first row, which my wife Payal doesn't like to sit on. Actually, I don't like myself also, but it's good she's not here. 0, 1. Can we get tickets before? 0, 1. Can we get, what was this? Babysitter trailers. Okay, we can watch the trailers. We can don't watch the trailers, watch the trailers. That's 0, 1, 2. So now I have more input variables to make this prediction better, which is that whether we will go or not. So now my Y depends upon sum of x1, x2, x3, and x4. And I can have more, right? You can see life is complex and I can just start putting in there. But my son realized that some of these mattered more than others. So sometimes he realized that, he cares about these trailers, but he cares less about these trailers. Then he cares about the tickets, but sometimes these people are crazy. They will go and watch the movie sitting on the front row also. So he gave lesser weights to these tickets. He said, you know what? Let's give lesser weight to tickets, like we get free tickets or not, like booked tickets. So he gave lesser weight to this, but babysitter was critical for him. And sometimes we even went without babysitter. So it was not like the deal breaker. We will take Aryan, me and my wife can take turns outside the theater and we can put Aryan to sleep and we can still watch it. Nobody stops us. And then we have trailers, and he said trailers, they care, but not that much. And can it be, is the movie running matter the most, right? So let's just take it, whether the movie was not running, let's just not talk about it because this is a premier condition. It was always true. So now I have, my equation becomes, what is the W1, W2, W3? So my equation on neural network became Y is equal to WX, while can I make these metrics? Can I put all the weights here, W1, W2, W3, W4, and all the X's here, X1, X2, X3, X4, and then Y can be a multiplication of these, which is this equation. And then I can represent it like this. Good, everybody following me? This is our new equation. And now we have a better way to represent how can we get to movies. And my son is pretty happy. He can make these predictions based on these variables, and he can call his friends that no matter what, these guys are not going because the score is. But then they have another problem, which is it 0 or 1? Because end of the day, this value needs to be 0 or 1, right? Like Y needs to be 0 or 1. But here, if you take the number is coming higher or closer to 0, so he needs some kind of a activation thing. And for that, he said, you know what? I will create some kind of function which will make this non-linear, because right now it's linear, it just goes up or down. Can I put one more thing that helps me predict it better? And he called it like an activation function, whether these will activate or not. And he called it ReLU6, which is if the values of this equation is more than 6, then only these guys will activate. Then I can mark this 1. If it is less than 6, then it's 0. Because he figured out that some of these needs to be more than 6 somehow. If it is more than 6, these guys always went. And now it's not more linear. He made it a little bit non-linear. And we can call this as more like an activation function. So I can improve this equation also. And I can say ReLU6. Great. We have activation functions. We have weights now in our equation, and we have inputs. Okay, Sneh is with me. I lost 7 of you because earlier I had 7 of you with me. So I know at some point I will lose all of you and then we will stop. That's the whole idea today.
Mahesh,
Yes.
what do you mean by activate?
Activate means when I want the value of this thing that is Y, which is whether I will go for movie or not, is 1. When can that be 1? And can I, earlier it was if it is positive, then it is somehow 0, but I wanted more, which is I wanted to little bit sophistication. I wanted to say if it is only above 6, then only activate. Activate means Y is 1. Deactivate means Y is 0. 1 means we are going for movies. 0 means we are not going for movies. Can I represent X1, X2 like these small dots?
Yeah.
And then Y here. And then Y, can I connect them like this? And then I can call this W1, W2, W3. Isn't this looks like a fancy? Now I'm talking like researchers. If somebody looks at this picture, then all of you will be like research students and I'm like professor. And this looks like a neural network. That's pretty much all the neural networks are. But let's make one more complexity. Then he grew up, he became 7, and then he wanted to see movies with his friends. Now he has 2 friends, Bishop and Brooklyn. Now he has his own preferences. He wants to go for movies, but he wants to go only when Bishop and Brooklyn will go. And there's one challenge that he learns now, that their equation has more parameters because their family cares about other things. Like we were picky about trailers, they are picky about something else. Hey, is it that day? Do we have to go to Sunday? Sunday is a church day for them, not for us maybe. So all these variables counted. So he added their variables. But there was another thing that mattered to him, that even if the value was above 6 or that activated, there was a bias to their action because Bishop Dad doesn't like movies at all. He hates movies. He just goes for his son's sake. While Steve here, Brooklyn's dad, just loves movies even more than us. So now he want to cater for that bias somehow in this equation. So what he does is he adds another thing in the end to add the bias, and he makes it a little bit more fun. And he says, maybe I need to learn about these families, but I don't know anything about these families. So what I will do is I will just add a hidden layer, and I will just put 3 parameters because 3. So he adds another layer, and then he puts it here. And right now we will call it a hidden layer. The idea is that I need to learn these patterns of these families. And now I added another layer, and I'm calling this another layer, which will find how these families activate. And for each one, I can add a number called a bias, B1, B2, B3, which helps me represent their own family challenges. So now I can say, hey, I can keep this bias value positive for Steve and negative for Bishop. Given the same variables, this family may not activate, and I can put it with the bias. This is bias for action. You can remember it like that. And all of us have a very different bias for action. Like Jui had it today. She is there in the middle of night in Singapore. So her bias is positive, while some of you are like already left the call and your bias to learn is negative. But all of us had it. And maybe you just left it because there was something else going in your life, which is more important. And that now my son can model it somehow, and we can learn that also. So our equation became great. This is pretty much a very sophisticated neural network at this time. It has inputs, it has hidden layers, and it has output, which is your 0 and 1. Now, actually, he learned that movies are not just movies. Movies also have a factor that do we like the movie? We have not even opened that box. So there are more parameters in a movie, and he started adding those parameters. And now he need to learn how different parameters in a movie, which is actors, actresses, directors, genre, all these also played a critical role whether we will go for a movie or not. The world is not as simple as that. If it is a Hindi movie, we will go. If he need to represent that in an equation, the number of inputs changed, and his hidden layers were no more able to accumulate the complexities or the patterns. So what can he do to solve this problem? So he has more patterns to find. This pattern was good for his 3 families, given the underlying condition was that we will always go for movies, but that underlying condition is no more true because we are picky, we only go for Salman movies, but we don't care about any other guy movies, even if they are good. And there are more complexities in that, right? We go for Salman movies because we like the music, we like the director, we like this, and we like that. How can we learn those patterns, or how can we break that, and something can learn that also now needs to change because the number of inputs changed. That means number of patterns changed. How can I change this network to accommodate more? One idea, just one idea would solve this. Anyone? Memory. Maybe. But how are we storing memory? We are going very down. What is the storage of memory? Last time we stored the memory by adding these small neurons, or these small new things by adding a hidden layer.
More hidden layers.
Awesome. More hidden layers. Can I add or number of these elements in a layer? So I can either scale vertically or horizontally. So more complexity in my world, I can keep adding more things. And somehow I am thinking that we will learn or we will store these patterns in these neurons. Neurons are nothing but a way to store numbers in these equations. And a network that connects all the neurons of one layer to the another is called a neural network. Okay, this is a random thing. So what my son did, he connected all these things together, and he created a very sophisticated network. And eventually this network was supposed to predict whether we will like or go for this movie or not. And we only go for movies that we like. So, okay, now we have an equation. And it's a pretty awesome equation. It can represent the world. It has non-linearity in it. It has weights. It has biases. So the world looks really cool. But the challenge is when he runs this, he gets a result that Mission Impossible actually we watched and Challenger we didn't watch. That's what his neural network is telling it. So he has the problem that he has the right representation of the world in a mathematical equation, and he can represent it, scale it with number of hidden layers, but it doesn't work. He need to make this learn. This is a non-learning static system, and weights and biases are random. Those random value need to change, and how can we change them? That's the problem. So he comes up with this idea of a cost function. What is the cost function? If I know what is the right value, which is 0, and if I can subtract what is the value my network gave, I can come up what is the cost of failure here, which is 1. In case of Mission Impossible, in case of a Challenger movie, also 1. I can take average of this, and the cost function is 1. That means my network is really bad. The worst network will have a cost function of 1. Ideally, you want the cost function to be 0, because I wanted to predict Mission Impossible as 1 and Challenger as 1, right? This is 0. So I wanted this to be 0, this to be 1. The subtraction should be 0 and 0, and that's my ideal state. Now he knows the answer. So for the value of y to be 1, he can go back and change the weights and biases and fit it. And then the value will be 1. Because weights and biases he came up with, correct? He has a full control on setting the weights and biases because he only got x from the world. He knows the y. He can go back and change the weights, value of weights and biases, then make this cost function to be perfect or lower. Then this equation becomes that we need a way to reduce the cost function here, right? So there is a cost function. And how can we change this, or how can we find the minimum cost function, is this idea of gradients. That's called the gradient, which tells you which direction will you move and how much will you move to change or reduce the value of this function. So let's say this is a linear function, and this is the minimum value. So if you put this equation, all of the values of weights and biases, I need to find a minimum value of weights and biases. I want to make weights and biases such that all the values of weights are here, all the values of biases are here, and this equation, final values are here. And I want to reduce the outputs. I want to find the minimum value, this value. So I can start here, and just imagine there is a math function called gradients, which helps you find the minimum value of this function at this point and tells you that, hey, if you move in this direction with this much, then you will find the next. So where you are and how much to move helps you find minimizing the loss function or the cost function. So if you can calculate that gradient, and these steps are called your learning rate, or at what rate you want to go down. So if I set these steps, this n as larger, then I can go faster to this place. But if they are larger, then I can take one step here and the second step will be here. Then I will miss the minimum point, but I need to take only 2 steps to find the minimum value, find the value of weights and biases, which will give me the value 1. But if I take very, very small steps, then I can reach very close to this point, right? Or sometimes hit it. But it comes at a cost that I need to do these many iterations or these many steps in my calculations. So that's the way how we learn. We can be fast learners, thinking fast and thinking slow. By the way, they had it like that only. They said that when they learned gradients, they learn gradients fast in the beginning and then they slow down. That's one of the innovation they did in neural networks modifications when we started training large language models. But for the today learn, all you are learning is, hey, how can we reduce? So I can put a negative sign that how can I find the value of gradient at for this function, which lowers the loss function or the cost function. And how I do that? I go back and change the weights. And then I set the weight for Mission Impossible. And now it is coming as 0. And then I go and set the weights for Challenger. And now it's coming as 1. And now I can set the weight for dabang. And then I can say set the weights and I can continue doing that. But every time I'm doing it, the other may not impact, right? That's the beautiful part of generalizing. And that's the learning in neural networks, that when you do that, you have to do it efficiently, that if it changes for dabang, it does not mess up Mission Impossible, right? So how much you should nudge, or how many much weights and biases you should nudge, is something that is sophisticated and needs to be optimized. And we have awesome ways to do them. They have a lot of best math equations to do it. We call them optimizers, which decide how much weights and biases should change so that we can learn the patterns without messing up the equation. One example of an optimizer is Adam. That's pretty much all I needed to tell you on neural networks. This is how the world works. The more movies I have, we call this label data. Once this whole model is trained and you got a good enough cost function, the good enough values that you can predict, you start making right predictions on this data. So this is called label data. Then you have this idea that you can divide your label data into three parts. Your labeled data can be your training data. Training data is the data that you use to nudge these weights and biases. And then you have your validation data. This is the data you don't change. That's the data you use to check what is the final value of cost function. Have we gone 1 or 0, or we are 0.75? If we are 0.75, we say our model is 75% accurate. That's the number you see in OpenAI releases when they say, hey, for this data set, we are now 75%. It just that means is that, hey, their cost function is 75% accurate to make the predictions that are known. So you train on train data. Those data you have set your weights and biases, so you should be close to 100% accurate. But then you test on validation data to check whether in real world, how will it perform? And then your test data is the data that you use to test your network based on your real network use cases. Gradient descent is this idea of finding the minimum value of the cost function. Local minima, maxima are another ideas, which is if your network is look like this, because the real world is not as simple as just this parabola, then you can find the minimum value here, but the real minimum value is here. So this is the local minimum value of this function here, but the global minima is here. And you have found only the local minima and you thought we achieved the market, we achieved success, but then you have to find global minima. And there are techniques for you to avoid local minima and reach to global minima. Adam has it where it shoots little higher so that it somehow goes and find the global minima. Gradient descent is this idea of descending a function to find where its cost function or its loss function is minimum. Parameters. People talk about 3 trillion parameters model, 7 trillion, 50 trillion parameter model. Parameters are nothing but weights and biases. These are the things that you can change in your learning process. The number of weights and biases in a model are the parameters in a model. The larger the model, the larger the parameters, the more patterns it can learn. That's why we are saying we need larger, and large language model is nothing, a model with more and more weights and biases. And why? And that's why it's able to learn how a doctor works, because it learns the doctor patterns, a lawyer patterns, an accountant patterns, because we keep on increasing the number of hidden layers. And then somehow we figure out how to train a largest model. And that's what OpenAI or Anthropic are paid for. They are still able to figure out how to train a trillion parameter model and not break this equation. That's what the researchers are getting paid $80 million salary. To train these models with continue to learn, and their parameters are trillion scale, trillion parameters. Our model had some 1,000 parameters, the one that we created. They have trillion parameters to deal with. A model is nothing when you say that, hey, this is good. Then if I can take a snapshot of all the weights and biases of this equation, this Wx plus B, at that point, what is the value of weights and bias matrix and X matrix? If I can just dump that, that's your model. This equation, the final equation of trained weights and biases that never change after that, is a model. That's GPT-5 for you. That's GPT-4 for you. It's nothing but that time the value of weights and biases is frozen in the world. After that, we don't change them. So what is inference? Inference is just sending your inputs and getting a value out. So no learning, just prediction is the process of inference. What is the training? Training process is two-step. It does forward, and then it finds out, compares it with some value, and then goes backward and adjusts the weights and biases. So the process of going back and forward is called learning or training. Activation function bias we talked about. So that's pretty much neural networks for you. I can take all your questions, but hopefully this was a little helpful. By the way, we have started the course, and the course is running. And if you are in the Wednesday batch, you already had your session. If you're doing the Saturday batch, then I'm going to see you tomorrow. Some people have a lot of questions. My team reached out to me that people have a lot of questions about, hey, what will you do? How you'll teach? This happens, this happens. So I'm going to do a free session on Friday. This is only, I'm doing it for our community. So if you're part of the community and you want to sign up for that free session, so this is just free session. You need not to pay or anything. Just show up. We will just talk about week 1. And you can decide for yourself. Instead of answering your individual questions, I will just do a free session.